All right, so for this last round of examples in section 4.5, we'll be starting with probably an equation that has some logarithms on one or both sides, and we're going to get rid of the logarithms. So the most basic kind has logarithms of the same base, on both sides. So if log base b of x equals to log base b of y, the fact that log base b is a one-to-one function tells us that then x must equal y. But if we want to kind of see this more concretely, if we start with an equation of this form, log base b of x equals log base b of y, what we can do is exponentiate both sides. What does that mean? That means, right, b to the log base b of x equals b to the log base b of y, right? So take both sides and make them the exponents of an exponential function whose base is the same base b. That's what it means to exponentiate. So once we see this, you know that the inverse property of exponentiation and logarithm is going to give us that x equals y. Because here, this side simplifies to x, and this side simplifies to y. So in this first example then, they give us log base 2 of 5x minus 3 equals to log base 2 of 3x plus 11. So we have the same base on both sides, right? Base 2. So we will exponentiate both sides with base 2. So that gives us that 2 to the log base 2 of 5x minus 3 equals 2 to the log base 2 of 3x plus 11. But then these operations undo each other, and we're left with just the exponents now, or sorry, just the inside of the logarithms now. So we have that 5x minus 3 equals to 3x plus 11. And this is routine from here, I think. We have add 3 to both sides, we get 5x is 3x plus 14. Subtract 3x from both sides, we get 2x is 14. And divide both sides by 2, we get x equals to 7. Okay, in the next example, it's a little bit more funny. We're given log base 3 of x equals to 2 plus log base 3 of x minus 1. Now recall, we don't have here that just one logarithm on each side. We have this extra term here, so we'd like to realize it somehow as a logarithm. So let's recall that 2, this number that's extra here, equals to log base 3 of 9, since 3 squared equals 9. So now we can rewrite the equation at hand as log base 3 of x equals to log base 3 of 9 plus log base 3 of x minus 1. And now we can use one of the logarithm rules to simplify the right side of the equation. So this becomes log base 3 of x equals log base 3 of the product, 9 times x minus 1. Okay, and now we can rewrite that as 9x minus 9 inside of there. That's fine. And now we have one of these nice equations with this logarithm of the same base on both sides. So we can exponentiate both sides with base 3. And we get 3 to the log base 3 of x equals 3 to the log base 3 of 9x minus 9. Okay, but then these two operations undo each other, and we're left with just x equals to 9x minus 9. So we can subtract 9x from both sides, and we're left with minus 8x equals minus 9. So then we can divide both sides by 8, and we're left with x equals to 9 over 8. Very nice. Okay, and now let's see, 2 more examples here. The next one gives us natural log of 4x minus 1 equals to 5. This one we will exponentiate both sides with base e. So we have here e to the natural log of 4x minus 1 equals e to the 5th. And now on the left side, the two operations undo each other, and we're left with 4x minus 1 equals e to the 5th. Now notice, this one is just a number. It might not be a very nice number, but it's just a number. So we'll just treat it like a number to go forth and solve for x. So we'll add 1 to both sides and then divide by 4. And we're left with final answer being x equals e to the 5th plus 1, all divided by 4. Okay, and as a last example, we get something practical. Very nice. So we have our good friend Bob here again. And Bob invests $2,000 at 4% interest compounded monthly. And they want us to know how long will it take for this bank account to increase to $2,500, I guess, just by having the interest. He's not going to put any more money in it. He's just going to let the interest accrue there. So we can harken back to, I think it's section 4.2, where we met the compound interest formula. But what we want is our new amount to be 2,500. And our compounding period, we have 12 compounding periods a year because we have 12, because it's monthly, sorry. And our interest rate is 4%, which is 0.04. So, the equation now will be that 2,500 equals to 2,000, the initial amount invested, times 1 plus 0.04 over 12, all to the 12t. And so this t is now given to us in years. And so this equation is actually a little bit different than the ones that came before it. This is more of just an exponential function equation. So this is going to be similar to some of the ones that we saw from the second video in this series on section 4.5. So we have an exponential function on the right side, and we'd like to isolate that exponential function and solve for this variable t. So let's isolate the exponential function part by first dividing by 2,000. That gives us 1.25 on the left equals to 1 plus 0.04 over 12 to the 12t. Now, I'm hesitant to make a decimal for this 0.04 divided by 12. I want to keep it exact until the very end, because this can get a little bit dicey if we don't. So now we have our exponential function, though, isolated on this side. So we can take natural log of both sides to get rid of the exponential function. And so we'll have natural log of 1.25 equals natural log of the quantity 1 plus 0.04 over 12, all raised to the 12t. And we know by the logarithm rules that we can yank this 12t outside here. So really we have natural log of 1.25 equals to 12t times natural log of 1 plus 0.04 over 12. Now we'll solve for t, isolate t. So this number here, natural log of 1 plus 0.04 over 12, it's not a very nice number, but it is just a number. So we can divide both sides by that number and divide both sides by 12 as well. And so we're left with that t equals to natural log of 1.25 divided by the product 12 times natural log of 1 plus 0.04 over 12. And taking to the Texas Instrument, this gives us that t is roughly about 5.59 years. Okay, that's what t is always given in years in this model. We have the number of compounding periods per year here, and this is number of years. And so if we multiply this guy by 12, we can ask about how many months this would take. And the answer is about 67 months it would take for Bob's money to increase by $500 here. Okay, so that's that. Stick around for the next talk, which will be the last one about exponential functions, and it will be about exponential modeling. So we'll see you then.